Hello, good evening. My name is Scott Grizzard. This is Calculus 1, the 12th of October, 2020. And tonight we're going to be talking about linearization and I said linearization and its discontents, right? And all the little things that are implied by linearization. So, linearization at first seems like something a little minor. And you don't need a lot to do the problems that, when you want to do the linearization. The problems, I don't want to say they're simple, but they're not the more complicated problems. Once you understand the idea of what it's doing, kind of getting at these problems is, as long as you can take the derivative, is fairly quick. But it's actually a very deep concept, and it's a lot deeper than it looks like. So it looks like at first that all you want to do is take an estimate, but it's a lot more than that, and that's the idea that I want to show you today. So anyway, so that's where we're going tonight. As usual, we have chat and Twitch. Over there, we have chat and Discord. We have a TA that just waved her hand at me. And we're good to go. So let's go ahead and let's talk about what we're doing. So let's see here. We've got here. So as I was saying before, so last time we did related rates, and those are important. It's a nice thing. But here tonight, what we want to do is we want to kind of go through these, just show what all this little idea of estimate with linearization all just implies. So we have all this stuff that we kind of want to go through kind of in this direction, if you can see that. And we want to talk about linearization itself. And then the idea of getting better estimates through Taylor polynomials. Then we want to kind of play with L'Hopital's rule a little bit, because one of the implications of this thing is L'Hopital's rule. This is a module 3 thing. It's one of the first things we do when we get back, but it's really it stems from linearization. So this is the time to talk about it. And then we ought to talk about differentials, which are a very intuitive way of approaching the derivative. And through differentials, we can very quickly get at inverse functions. So in other words, if you have the derivative of a function, you have the derivative of its inverse if that exists. You just do 1 over that. And then we'll get into concavity and convexity, and all of these things that are the big ideas of Module 3, or at least the first half of Module 3. So, and these are all defined formally in terms of the linearization. It's kind of so if you get this linearization concept, there's a lot of stuff, not only, obviously the questions are now, but a lot of the formal stuff that we're going to be doing later in the course, at least in Module 3, just kind of comes back to this idea of linearization. So let's look at it. So the big idea is, let's talk about f of x equals e to the x. Now this isn't the perfect thing to use because it is its own derivative, so sometimes the example can be a little confusing. We can also consider sine of x as another example. So we'll have that one floating around here. Now, e to the x is kind of a pain to work with, especially for decimal things, right? So its graph, let's pull up Desmos here. Its graph, looks like this. And so, let's see, I want screen. So here's its graph. And it's kind of, you want e to the 0.1. Okay, and that's kind of a pain. Suppose I want to talk about values near 0. Okay. So what I want to talk about is the stuff that's, I zoom in quite a bit, and I want to talk about stuff like 1.01 and 1.02. And I'm doing, the idea is that I'm doing science, which, I've got some like error in the measurement anyway. And it turns out that this is, has deep, profound ideas for math as well, but it was kind of a science idea. So I want to talk about values near 0. Is there something I can do that, close enough for government work? Is there something close enough for government work? So you can imagine that what I've got is a video game. I'm calculating a whole bunch of particles, and I don't want to spend a whole lot of cycles calculating e to the x, because the algorithm, it's not hugely expensive, but, it's a little expensive. But I know I'm in this neighborhood. So again, the point is that I'm in the neighborhood of 1. So here's the idea. The idea is that I'm going to take, that didn't work. The idea here is what I'm going to take is just a little bit. There we go. The idea here is that I'm going to take values that are kind of close to 1 and talk about them. I'm sorry, kind of close to 0, x equals 0, and talk about them. Okay. Let's move. You're in the way. This idea here is different than this idea here. All right. This is all linearization. Okay, so around 1, if I come over here and I make a line, kind of the best idea is this tangent line right here. And what I'm going to do is I'm going to define a function. So I'm going to define let me write some of this stuff down, what I stole here. F of x equals e to the x. And this green line is L F 0. This is x equals 0, by the way. There's the thing, y equals 1. And the idea here is that I have a function, right? I have this equals f of 0 plus f prime of 0 x minus 0. So when I do this, f of x equals e to the x. So LF0 of x equals f of 0 plus f prime of 0 times x minus 0. Well, f prime of x is e to the x because it's e to the x. So I wind up with e to the 0 plus e to the 0 times x minus 0. Well, x minus 0 is a nice number. That number is called x. And e to the 0 is 1, and e to the 0 is 1. So I wind up with 1 plus x. Now, I don't care how fast your e to the x algorithm is. There is no way that a computer is going to calculate e to the whatever, e to the 1.001 faster than it's going to calculate 1 plus 1.001. It just can't do it. So f of 0, So f of 0.001 is about 1 plus 0.001. Now, if I actually ask, let's ask Google here, what e to the 1 to the 0.001 is. The actual answer e to the 1.0, I'm sorry, e to the 0.001 is actually, decimal approximation. So this is from the calculator, 1.00100050017. So isn't that close enough for government work? Well, the linearization LF0 of, so this is actually LF0 equals LF0 of 0.001. Well, LF0 of 0.1 equals 1 plus 0.1 equals 1.1. So, right, so that is the approximation for e to the approximated using linearization. Okay. And then L of, in the calculator, e to the 0.1 is 1.0, I'm sorry, 1.10517, blah, 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 using calculator. So, sure, I'm a little off. I'm not that off, right? Here is my linearization. Oops. So here's the screen here, right? And if I zoom out, I'm off, right? If I'm at 1 here, and I use this linearization to calculate e to the x, I'm going to be, almost a whole unit off, right? Like 0.8. However, if I zoom in here, right, if we're talking about this number right here, does it really matter which function I'm hitting? Depending on your scale, it's close enough for government work. How do we feel about that idea, 1 to 5? I'm using the equation of the tangent line as sort of an estimator. Okay. So big idea, I'm using the equation of so big idea. I am using the line tangent to f at x equals a as an estimator. Okay. And that's sort of the big idea about what I'm doing here. Let's do that other equation now. Let's do, you're actually seeing the stuff that I'm talking about later. I made notes ahead of time so I could drag and drop. Let's look at g here. G of x equals sine of x. So let's plug that in. And let's talk about what's going on around pi over 2. All right, so let's make an estimator. So let's make an estimator. So what I want to do is I want to make an estimator for this function here around sine. Okay. So what I'm going to do is I'm going to take the derivative. So g prime of x equals cosine. And so what I'm going to get is this. So I'm going to get L of g at pi over 2 of x. My estimator, okay. I've got g of a, which is pi over 2, plus g prime of a, which is pi over 2, times x minus pi over 2. Now, again, sine, cosine, these things are a little bit funky to deal with for the computer. But a line is a line. That's easy to compute. I can compute lines very, very quickly. So let's do this. So I've got g here of this, so sine of pi over 2, plus cosine of pi over 2 times x minus pi over 2. Well, the sine of pi over 2 is 1, but the cosine of pi over 2 is 0. So what this says is near pi over 2, you might as well just use the value 1. And that's as good as you're going to get. Right? Does that make sense? So what this is saying is that near pi over 2, I might as well use the value of 1. Oh, I don't have it. How do you do that? I think you have to put in y if you want that. Yeah, there we go. So, well, if I move away from this, I'm going to be, so here's 1.8 and there's 0.972. That's 0.028 off. Right? So as long as I'm near pi over 2, I might as well use the number 1. I might as well use this line. Okay? Let's do a different one. Near 0, near 0, it's going to be a different story, right? Well, near 0, I've got g of 0 plus g prime of pi over, g prime of 0 times x minus 0. We always love that one, right? Because x minus 0, that's easy to deal with. Okay, this equals sine of 0 plus cosine of 0 times x, which equals 0 plus 1 times x, which just equals x. So this says I just use the line x when I'm hanging out around 0. Okay. Leave it here for just a moment. So this says that I might as well just use the line x when I'm hanging out around 0. So how do we feel about that 1 to 5? LG of 0. Okay. So that's the idea behind linearization. It's a linear estimate based on the tangent line. Okay, so if I wanted to estimate sine of 0.1, I go LG0 of 0.1 equals, well, 0.1. And it basically says that, I get close enough, it's good enough for government work. Well, let's look at this problem a little bit more. Okay, so let's switch back here. I can do better. If I could take more derivatives, I can do better. So let's say this is not good enough. All right, so that's linearization. Now, let's say this is not good enough. Can I do better? Can I get a better estimator? And the answer is yes. Let's slide on over here, and instead of this, all right, so keep this picture in mind. Now, can I get a better estimator? The answer is yes. I can if I'm willing to take more derivatives. So this is the best estimator you're going to get with only one derivative. And if you've got, data that's, a little bit spread out, especially if you're doing something like a social science, like, economics, although whether economics can even be called a science is another issue. I have a master's in economics, so I'm allowed to gripe on economics as a profession and as a science. I'm allowed to. I have a degree. But, if my data is kind of spread out, right? If I'm talking about demand curves, a linear estimate of a demand curve, especially if I'm talking about moving another 12,000 units, that should be good enough, right? But can I do better? And the answer is yes, I can. And this is called a Taylor polynomial. This is called a Taylor polynomial. Okay. And it's important to note that while this is in the material that life science calculus has to deal with, it's not in yours until Calc 2. But I'm just going to show it to you because you sometimes see it in physics with Calc before you see it before you're supposed to see it in Calc 2. So I want to show it to you just in case you wind up in that class, and I want to show it to you anyway, just so it's in the back of your mind, that it's there, that you can do better estimates. But the main reason I want to do this is sometimes it shows up in physics before you get it. Okay, so what I'm going to do is I'm going to say let n be some positive integer, and f be differentiable n times. So what we're going to wind up with is this. Okay, that x shouldn't be there. Bad x. So what we're going to wind up is this. What we're going to do is we're going to take f of a, which is, just how we started. Now notice here that this term right here, f prime of a, x minus a to the first. First thing to notice L f a of x equals t 1 f a of x. Okay, so the first degree Taylor polynomial is the linearization. Okay, so let's look at the second degree. All right, so the second degree, t2 f a of x. This is the second degree, would equal f of a plus f prime of a over 1 factorial, which is 1, x minus a to the first, plus f double prime of a times x minus a squared, all over 2 factorial, which is just 2. And that's it. This is the second degree. Polynomial. And often this is all you really need in order to do really nice stuff. Okay? Lenses get, the lenses get ground not on the actual sine and cosine of things. They usually use the second degree or third degree polynomials to grind lenses in the computer programs. That's close enough. In these pairs of glasses, they probably used the constant term alone. Okay. But, if I spent money, they'd add more degrees to the polynomial. All right, so let's look at what that is. So let's let f be sine. So this is just an example. Let g of x equal sine of x as it was. So I'm going to need a little bit more here, right? I need g prime of x equals cosine of x, and g double prime of x equals negative sine of x. Now, staying centered on 0, the second degree Taylor polynomial is going to be g of 0 plus g prime of 0 x minus 0 plus g double prime of 0 x minus 0 squared over 2. So that is going to be sine of 0 plus cosine of 0 times x plus negative sine of 0 times x minus 0 squared over 2. So this equals 0 plus x minus 0. Not so helpful, right? I didn't really get anything out of that. Let's go again. So this was T2. Let's go for T3. And now I'm going to get G. So now I'm going to get sine of 0 plus cosine of 0 times x minus sine of 0, which is going to be 0 again, x minus 0 squared over 2 plus, minus g triple prime of x is going to equal negative cosine of x minus cosine of 0 times x minus 0 cubed over 6. And that is going to equal 0 plus 1x minus 0 minus x cubed over 6. Okay. So let's plug that into our other function. So let's go back and let's look at that. So I'm going to plug in here. Let's put it back on the other one. This is my new estimator. X minus x cubed over, oops, that doesn't make sense. X shift cubed, there we go, over 6. And look what happens here. Here's sine in red. Here's my linear estimator in blue. And look what happened here. Look at the green. See how close that, I mean, that works all the way up here. Okay? So how do we feel about that 1 to 5? If I add some more of these derivative terms, I get close. I get more useful space. I get more accurate things closer, and then I've got, usefulness farther out. All right. Well, let's do one more. We already did e to the x before. So let's look one more at them. Let's look what happens if I plug in e to the x again and do the same pattern thing here. So I've got e to the x, and our first one here, our first polynomial, way back when, was 1 plus x. So there's 1 plus x. This is all centered on 0. And now let's take another so let's take another degree. So let's do the second and then the third degree polynomials. So here we go. I've got f of x equals, that's where that x came from. F of x equals e to the x. So my second degree is going to wind up being 1 plus x squared over 2. And my third degree is going to wind up being 1 plus x squared over 2 plus x cubed over 6. Okay? So let's sub those in here. Let's do 1 plus x squared. I'm sorry, 1 plus x plus x squared over 2 and then let's do 1 plus x squared over 2 plus x cubed over 6. And look what happens. Okay. Here's e to the x. Here's my first degree polynomial. That's the line. Here's my second degree. Look how this works here. Look, you know, it's not, you know, it's a quadratic, so it's this thing speeds ahead here. It's too high here. But you know, it's a little bit better. I get a little bit more range. Before, I would have had absolutely, you know, I go over to 1, I get horrible. Now my distance between my polynomial, when I'm estimating a whole unit away, it's not that bad. And look what happens when I go for the third. There's the third. I mean, the third kind of diverges because it's heading the wrong direction on the negative side, but look at it on the positive side. I could get good estimates in this direction all the way out to about here. Especially if what I'm doing doesn't require a whole lot of accuracy, right? It's an explosion on a video game that needs to render quickly. So it's got a ton of particles moving very quickly. How do we feel about that 1 to 5? Okay. So let's go back, right? Let's go back to linearization. That's just a kind of preview about what's going to happen in the future. Let's look at something else, okay? Let's look at L'Hopital's rule. So let's say I've got this other problem here. So this is another application of linearization. Come here. So let's look at L'Hopital's rule here. So this is another application, another I am showing the correct screen. Nope, I'm not. So this is another application or another implication, really. Okay, this is L'Hopital's rule. Let me zoom in here. So let's say I've got the problem, all right? Here's my problem. I want to take the limit as x goes to pi of this thing. How the heck am I going to get at that? Right, because sine of 2 pi is 0. And 4x squared minus 4 pi squared, I throw in pi for here, I'm going to get 0, right? This top thing goes to 0, and this bottom thing goes to 0. Now, so I'm left with this idea, okay, how do I do a u sub? It's actually not that bad, right? You can figure it out. You figure it out because sine of u equals sine of u plus 2 pi. I can actually do it that way. So what I'll do is I'll add 2 pi to the top. Right, because sine is periodic over this thing. So I can do this. Limit as x goes to pi of sine of 2x plus 2 pi over 4x squared minus 4 pi squared. And then I do a difference of squares on the bottom, right? And then I do blah, 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 right? I have to do all these steps, right? I can do it. I get a difference of squares on the bottom, then I let u be that piece of it, and then I pull out the other stuff, and I separate it all out with the product rule, and then I can do it. Can I separate that out with the product rule? Anyway, I can't do something about this. But why? Okay? Let's not do that. Let's instead look at it. Okay, so what does this thing look like? Let's do this. Sine of 2x. Let's look at the top and the bottom separately. I actually want to keep that graph. So let's do Desmos again. Graphing calculator. So let's do this. So let's do sine of 2x on the top. And on the bottom, we've got 4x squared minus 4 pi squared. So here's what it looks like. I'm going to zoom in here so this thing flattens out a little bit. Let's see. There's a way for me to like do just one of them. There it is. All right. So there's pi. And you can see what's going on here, right? As I get, this is, the bottom here. The bottom goes to 0 here. And so does the top. So 1 to 5, how do we feel about this idea that the bottom and top are both going to 0? Right? They're both heading for this. Someone's asking for this class, should we know how to do Taylor polynomials? No. You need to understand the concept. All right? This is an idea that's supposed to be floating in the black of your brain. All right? I'm gonna actually write that down. Okay. Don't worry about the formula for my class. I just want you to understand the concept that I actually can do better. But I have to keep taking more and more derivatives. All right, back to this. So I've got this idea that right here I'm going to have some issues. But if I give a little bit of a nudge, here I don't have an issue, do I? If I move just a little bit off, I get away from the issue. Just a little bit away, and I get away from my issue. Okay? So let's see. So over here, if I could get just a little bit away. So this is, I'm going to call the top P. What was it again? Sine of 2x? Right, this is the top of this function. And this right here is the bottom. This was, I'm going to call this Q of x equals what was it? 4x squared minus 4 pi squared. Right, so f of x equals p of x over q of x. Now, if I could just move a little bit away, from this from pi, I'd be good. In other words, if I could move to 3.14, because 3.14 is not pi. 3.14 is a rational number near pi. If I could take these values at 3.14, I'd actually be okay, because neither the top nor the bottom would be 0. 1 to 5, how do we feel about that? Just a little bit away, I'd be okay. Okay? Just a little bit. So I'm going to do that. But I'm going to do it in a kind of clever way. And let's look at this. Okay? So we've got p of x equals sine of 2x. And we've got q of x equals 4x squared minus 4 pi squared. Let's look at their linearizations at pi. LP at pi of x. What is that? Let's take the derivative. And I'm going to wind up with 2. I'm going to do a chain rule, and I'm going to wind up with 2 sine 2x. So the derivative of the outside is cosine of 2x. So the derivative of the outside is cosine. I'm going to get cosine of u times du over dx, and du over dx is 2. And q prime of x equals 8x minus 0. Since this is constant. How do we feel about those derivatives 1 to 5? Okay. All right, so we've got these nice little things. So the linearization of p at pi of x is going to be p of pi plus p prime of pi x minus pi. And the linearization of q of pi of x equals q of pi plus q prime of pi times x minus pi. But look at the ratios. Now, look at something else. The limit as x goes to a here. As x, what is the limit of the top as x goes to pi? What is the limit as x goes to pi of this? I don't need this piece. I need a limit sign. Take 3 points off my paper, or 1 point. Right, so I sub in here because this is a polynomial, and I'm going to get p of pi plus p prime of pi times pi minus pi. Right, so I wind up with p of pi because this is 0. And then the limit as x goes to pi of LQ pi of x equals the limit as x goes to pi of q of pi plus q prime of pi times pi minus pi. There's pi minus x minus pi here. Erase. It's not erasing. It'll be that in a minute. Equals directly substitute in for the pi, and I get q of pi plus q prime of pi times pi minus pi, when this bit is 0, so I end up with q of pi. All right? But if I take the limit of the ratios, let's look at this. So if I take limit as x goes to pi of LP pi of x over the limit as x goes to pi, let's assume I can do this. All right, so let's just take the limit of the ratios. I'm going to take the limit as x goes to pi of this. I'm going to kind of do equal-ish. All right, I'm hand waving a bit. We will do a more formal proof of this later. So this right here, I'm going to wind up with p of pi plus p prime of pi times x minus pi all over with a limit sign there. Excuse me. Over q of pi plus q prime of pi times x minus pi. Now, here's my question. What is p of pi and q of pi? Well, we'll sub it in. Limit as x goes to pi of sine of 2 pi plus, let's see, 2 cosine of 2 pi times x minus pi over q of pi, which was 4x, so 4 pi squared minus 4 pi squared plus 8 pi times x minus pi. What is this piece here and this piece here? Both of these equal 0. Well, that's convenient. Because both of those equal 0, I get the following. I get 0 plus 2 cosine of 2 pi x minus pi over 0 plus 8 pi x minus pi. Well, that's nice. Those things are 0. They go away. And now everything's being multiplied. Goodbye. And that is just a constant as far as the limit is concerned. So the limit sign goes away, and I'm left with 2 cosine of 2 pi over 8 pi. And if you'll recall, that was p prime of pi over q prime of pi. How do we feel about this 1 to 5? So I can think of the if both, so what I get is that if everything goes to 0, note this hinges on that fact. Note so in general, I have this. By the way, these are quotes by the equal sign because I can't actually do this because this is division by 0, this is division of 0. So I'm sort of saying equals-ish here, just as a thought. But that's the idea. I take the ratio of the linearizations, and I wind up with the ratio of the derivatives. It's a thought. Okay? Just equal-ish. Just keep it in mind. We'll call this diet L'Hopital. Okay? If f of x to 0 and g of x to 0 as x goes to a, and that's 1, and g prime of a and f prime of a both exist, and neither, and g of x, and this is the diet version of it right here, because normally I don't require g prime of a to not equal 0, but for the moment I am. Then the limit as x goes to a of f of x over g of x equals f prime of a over g prime of a. Later when we do the proof, we'll probably just do the diet version, the full proof of this later. But this is kind of just diet, because I can't have the full power. Normally I could take L'Hopital's rule again and again and again. Okay, but I don't have that yet. This is diet L'Hopital's. Just 1 calorie. Just 1 derivative. Diet. Just 1 derivative. You can do it again and again and again. Well, that's kind of cool. And L'Hopital's rule, which we'll get into more, is a direct consequence of linearization. Okay, let's talk about differentials. So imagine I'm going to give x a little nudge. So let's look at y equals x squared. Right? And let's imagine we want to give both x, we want to give x a little nudge and see what happens to y. So what I'm going to do is I'm going to implicitly differentiate weirdly. What is the nudge if I nudge x a little? So what I'm going to do is I'm going to implicitly differentiate like this. I'm going to do dy equals no dx over dy, no dy over dx, just dy equals 2x dx. So what I've done is I've nudged x a little bit and I've nudged y a little bit. Let's look at a different one. Old favorite, x squared plus y squared equals 1. Let's do the unit circle. So what I'm going to do is differentiate both sides strangely, kind of implicitly in terms of both. So I'm going to get 0 equals 2y dy plus 2x dx. How do we feel about that 1 to 5? What I've done is just after every time I encounter a variable, I take the derivative and I throw the dx, dy, du, dw, d alpha, whatever it is at the end. That's all I'm doing here. Okay. Now solve for dy over dx as if it was a fraction. Okay. Well, let's do it. Right? I've got dy equals 2x dx, implying that dy over dx equals 2x. Here, I've got 0 equals this. Now I'm going to do, okay, well, that means that negative 2y dy equals 2x dx. And then what I'm going to do is I'm just going to divide both sides by 2x here. I'm sorry, divide both sides by dx and divide both sides by 2y. And I get dy over dx equals 2x over negative 2y. How do we feel about that? That's a little strange. Okay. But note, there was nothing really special about solving for dy over dx when I did this. why not dx over dy? Why not? What's wrong with that? So to go back, let's say I've got y equals x squared. So I get dy equals 2x. So this should be 1 times dy, actually, because the derivative of y with respect to itself is 1. So I get 1 dy equals 2x dx. And I wind up with the thing that I wind up here. I instead of solving for dy over dx, I solve for dx over dy. So I throw 1 over 2x on one side. I don't want to do that. Yes, I do. I want to put 1 over 2x on this side. I'm going to divide both sides by dy. Yeah. Well, recall x equals the square root of y. Or square root of y-ish. If y is greater than 0. Let's see, what do I need here? Yeah, y will always be greater than 0. If it's plus or minus, right? So let's just do the positive. All right. I should have picked cubed root to make this work nicely. I picked something where I have to deal with the domain. Right, so I've got x equals the square root of y. So that means that dx over dy equals 1 over 2 root y. In other words, I started with y equals x squared, and then solved for dx over dy to find the derivative of the inverse. Let's do it again. Let's do it one more time with y equals x cubed. And yes, you might be saying, well, why don't I mean, we've already showed us how to do this when we did implicit differentiation. Yes, I did. All right. So you don't actually have to do it. You can do implicit differentiation on both sides and get the exact same result. Okay. I'm not saying that at all. All right. I'm not saying that there's anything wrong with starting with the square root of x and then doing what you would normally do to implicitly differentiate that. All right, I don't want you to get I don't want you to get the impression that this is somehow required. All right, it's so if you find it confusing, just forget about it and go with that. But the point is, and it should also be noted that a lot of the instructors don't like to do this because these things are not well defined at this level, if that makes sense. The differential is not really well defined. It takes a lot of time, but I can think of it this way. And the intuition is to think about it this way. What I'm doing is I'm just giving a little nudge. So if I give a little nudge to y, if I ask what happens if I nudge y just a little bit, I'm going to get 1 times dy equals 3x squared dx. So that means if I solve here for dy over dx, so I get dy over dx equals 3x squared. Okay, we knew that. And I get dx over dy equals 1 over 3x squared. The takeaway is this. Okay. Dy over dx, sorry, dx over dy equals 1 over dy over dx. In other words, it does work like a fraction. Okay? Or if f and g are inverses, so in other words, this thing takes x, f takes x to y, g takes y to x, then I have the following. I have f prime of, sorry, I have g prime of y equaling 1 over f prime of x. Or g prime of f of x equals 1 over f prime of x. That's all the same. How do we feel about that 1 to 5? I know I'm playing a little bit fast and loose, and that's intentional. The idea here is to gain intuition. And this idea of linearization actually gives us this. So if I want to take this back to linearization, right? How do we feel about it? Okay. Let's do one last little thing. Let's talk about concavity. Let f be differentiable at a. At x equals a. I'm supposed to do that. I think it's silly, but I'm doing it. Okay. Here's the idea. All right. F. So I've got some graph here. And I've got some line. And here it is. Here's A. F is concave down at x equals A if there is some neighborhood A minus delta, A plus delta, right? Some open neighborhood so that for all x in A minus delta, A plus delta, f of x is less than or equal to L f a of x. In other words, if I go to the tangent line at any of these points here, if I go to the tangent line at any point here, the function is below the tangent line. Okay, that's the formal definition of concavity. This is going to be in Module 3. This is going to be a big thing in Module 3. But it's a direct implication of linearization. It gives me that formula, right? I've got f of x is less than the linearization. Okay? So I get a formal definition for this idea of concave down. Concave up, as you can imagine, is that sign flipped. 1 to 5, how do we feel about that? Okay, so tonight we kind of talked about linearization, and the thing that you need to know for the test is how to do these estimates and how to draw these lines and make sure that everything kind of works out. Okay, now the stuff you need, so this is the stuff right here. The big stuff for the test is here. Not that, here. There's the test 2 stuff. We'll get rid of this stuff here. Maybe faster to just do this. There we go. All right. So the test 2 stuff is up to here. Then what I wanted to do is I wanted to talk about kind of some of the implications that you may see in the future, especially if you're doing physics before you take Calc 2 or finish Calc 2. L'Hopital's rule is going to be the first thing we really talk about for Module 3 after we take the test. And it's a direct implication of linearization. And then there's this differentials way. And I can do this. So if you like this, you can absolutely use this on the test. If you prefer implicit differentiation by just stating the derivative after each one, by all means, right? If you just want to go for it, go for it. And then we've got this kind of inverse function idea, which is technically on test 2, but it has never shown up. So if something does happen, I will like, hey, she put it on there. But she, again, it's never shown up before, but it is technically on test 2. And then there's this idea of concavity, which we're going to pick up in Module 3, which is going to be one of the 2 main themes of Module 3. And that puts the cap on the material that's in test 2 on the test. Okay? So we talked about Taylor polynomials, L'Hopital's rule, differentials, and inverses. And we talked about linearization. Thursday, and that puts the cap on test 2 unless there's something that I didn't know was going to be on there that winds up on there, in which case I'll cover it Thursday and I'll give you a heads up about that, or I'll cover it Tuesday evening special session, something like that. Thursday, we're going to be talking about functions of inverses, calculus of inverses. We've actually already started. We're going to flush this out a little bit more. We actually started talking about it tonight. And then we're going to talk about the inverse trig functions, their domains, and their derivatives. Are there any questions? And I'm over time, so. Okay, well, that's it for me then. I will see you guys later. Good evening.